pretty nice day. Not so bad finishing up this session of summer courses. How many summer courses are you taking? Three? Wow. That's quite a bit. That looks better. You are a brave man. Attempting to graduate early without an internship this summer. You know, that's a good plan. If you're not doing an internship, why not load up with some summer classes? Good for you. Anybody else taking a couple summer classes? Phil says, I like having a social life. Yeah. You know, it comes and goes in seasons. And working to enjoy nice things. Man. You have this and 376 right now, Olivia says. Would be nice. This little thing called COVID came around. Yeah, I haven't heard of that. I don't know what that is. 311 and APY 106. Does that mean you're taking summer classes next session as well? Phil says, I've been in school for 16 years part-time, getting this third degree done. This is your third degree? Olivia has a total of 4 classes this summer. Oh my goodness. You are also very brave, very hardworking. That's impressive. My hat's off to you guys. Very hard workers. Phil is a glutton for punishment. That's a lot of school. Next, you're going to be coming back for your 4th degree. You're addicted. Guys, we're going to do an experiment today. Added mechanical this summer for the dual MAE. Oh, were you aero? And now you're adding in mechanical as well? Check this out. We're gonna have an experiment with this motor. So you'll get to see this spinning as we collect data in real time on this monitor using Arduino, it's going to be like a juggling act over here. It'd be kind of fun. We just keep adding production value. Next, I want a green screen. I don't think it's too hard to make. I want one that you can, like, I don't know, put out and then collapse it down, put it in storage somewhere. I don't know. Are you guys ready to get started? Let's get into it. Was Project 1 okay for everybody? Is this gonna work? I have so much stuff on my desk today. Easy. Easy? Wasn't I office hours with you the other day? Well, you just had like a little tiny thing that you had to find. But you were in command. You had it figured out. That was a little stupid. Nah. Okay. I have so many wires on my desk today. Phil says consumed all the time I had devoted to the homework. It was a little time consuming, but now you're a pro. You could do a similar analysis like this. You're a pro. Okay. So this lecture is in danger of going a little bit all over the place. So I'm going to try to dial it in, focus it. But, like I said, we're going to do an experiment with this DC motor. And we're going to try to model the DC motor with a transfer function. Because I mentioned to you that transfer functions are good for getting a model for a system if you can do an experiment. So hopefully by the end of today, you can get a glimpse of what I mean by that. And one of the key components of that modeling process is the idea of a frequency response function. So the frequency response is kind of just what it sounds like. It's how a system responds differently to different frequencies of inputs. So today we're going to apply a bunch of sinusoidal voltage inputs to this motor, and we're going to see what it does. And that's called the frequency response of the motor. Okay. Well, let us start with like a little bit of review here. And we'll come back to this later. This particular transfer function. I picked it with a purpose. But, okay, so I have a first order differential equation here. And to give some physical meaning to this omega as a function of time, this is going to be in angular, let's say it's angular velocity in radians per second. And this v of t is our system input, and that is a voltage, and we'll just do it in volts, not kilovolts or anything. Okay, so let's say that the output y is omega, that angular velocity, and the input u is that voltage on the right hand side. Given those two, let's make a transfer function. So we've been practicing this a little bit. So the definition of a transfer function is the Laplace transform of the output divided by the Laplace transform of the input. And when you take the Laplace transform of a function of time, it becomes a function of s. And we like to write the variables with capital letters once they're in the s domain. I don't know who started that, but that's what we do now. Okay, so we want to get that function. So the, maybe I'll put a little box around this in the corner. So the first step in getting a transfer function is you take the Laplace transform of the differential equation. Okay? So I'll just write that out. So this is going to give us, oh, this is a capital omega, by the way. So that's what I'm going to use. S times omega of s, because that's what happens when you take the Laplace transform of a derivative. It's basically multiplying that variable by s. So that's the first term. Tau times omega s. That's going to be equal to k times v of s. And I already had a capital letter over there, so what the heck, we'll just leave it the same. Okay. Then I'm going to make this ratio omega s over v of s. What am I going to get? So I'm going to get k over s plus tau, right? Okay, sure. Where does omega come from? So that's just, when you take the Laplace transform of a function of time, we tend to write the variable that results in a capital letter. So omega is a Greek letter. So this little lowercase omega. So I wanted to write it as a capital letter. And that's what this omega is. Maybe I'll be really clear about that. Boom. Okay. So I have this ratio, but I want y of s over u of s. Well, I think y of s... Well, if we look at the definition of the output, it is omega of s. So, luckily for us, we have the transfer function. Right, let's put a box around it. Okay. So we're just continuing to practice this. That's how we get transfer functions from differential equations. Now I want to show you a block diagram representation of transfer functions. This kind of gives you a different way to visualize what a transfer function is. Okay. So I'm going to make a little schematic here. I'm going to make a block. And inside this block, I'm going to put our transfer function that we got from the previous part. So you can think of this block diagram as some kind of machine that takes in an input, which for this system, the input is v of s, and it gives you an output, which I'll call omega of s. And so when we think about how a system responds to different inputs, let's look at the step response. So I'm going to have my transfer function, my system, and let's say our step input with, let's give it an amplitude A. So the input as a function of time, let's say time is greater than 0, the input would just be this. So well, I guess I was using the variable v. Let's not use u. Let's make it v. So if I take the Laplace transform of a step input, we derived this last time. V of s is going to be a over s. Oh, is my pen being a... Okay. Hopefully the pin cooperates. Okay, so the input is a over s. Now this is how block diagrams work. The output is omega of s, But it's equal to this transfer function times the input that's coming in. So like when you see a signal going into a block, it's kind of like the two are being multiplied by each other. So you have this transfer function, and it's operating on your input by like multiplying these two in the S domain. And so it gives you your output. Let's do a couple more of these just so you can get a better idea. Okay, let's say V of t is a times t. So that's a ramp with slope a. So that means V of s is a over s squared. I'm gonna like separate these out. So I'm gonna have a over s squared going in to my transfer function, and out is going to come omega s is my transfer function operating on my input. Finally, let's say we have a sinusoidal voltage, which is what we're going to do for our experiment. So it'll be a sine omega t. Well, in this case, if you take the Laplace transform of that, it's a omega over s squared plus omega squared. So let's just keep going with this theme here. Think of it like Willy Wonka's chocolate factory. He has that gobstopper machine, which is veiled in a cloak, and it has raw materials that go in. And then that gobstopper machine operates on the raw materials and produces the output. Everlasting gobstoppers. You guys have seen that movie, right? I'm talking about the original with Gene Wilder. Okay. OG. Agreed. Okay, let's talk about this sinusoidal response a little bit. So what happens when you give a system a sinusoidal input? And I want to look at what happens at what we call the steady state condition. Well, this is also called it's related to the particular solution. If you remember, when you give an input to a system, you have a homogeneous part of your solution and you have a particular part of your solution. The homogeneous part of the solution decays to 0 after the settling time. And so all you're left with is the particular solution. And that's why we call it the steady state solution, because it's like, as I apply this input to the system, after everything kind of equilibrates and the homogeneous solution dies away, I'm left with steady state. So what does steady state look like when you just perpetually give a sinusoidal input to something? Okay, so we're gonna make a drawing. Get ready to draw. Okay. This is going to be our input, and it's going to be A sine omega t. So let's draw it. I'm going to put little boundaries on here. A perfect sinusoid. Okay, so the amplitude is this, the distance from the midline to the peak. And then this has an oscillation frequency of omega. Well, let's break that down. So this is one cycle of it. That's called the period. Well, omega is going to be 2 pi over the period in radians per second. And the period is in seconds. Okay, so this is just going to be perpetually oscillating. Like, it doesn't stop here. It's going on for all time. This is going to go into our linear system. So I'm going to draw the box. It doesn't have to be like the first order system that we derived in this set of notes. It could be any order linear system, okay? So this input is going in to this machine that we call a linear system. And what I'm gonna do, I'm gonna copy this because I want to recycle it. Let's see how this works. I'm going to kind of modify this a little bit first. Okay. This will pay off, believe me. It's going to be fantastic. Alright, what I'm going to do, I'm going to select this and make all of it kind of like a dull color so I can draw on top of it. Maybe we'll do that. Okay, you can still see it, right? Okay, so what's going to come out of the linear system? It's going to be a sinusoid of the same exact frequency. Let's draw this output. Let's say it's green. But usually the output delays the input a little bit. So it's like lagging a little bit behind. So the input's going up and then, okay, the output's starting to go up. And then it's coming back down. And then going back up again. Okay, now notice this. The amplitude of the output is generally not the same as the amplitude of the input. In this example, I made the output amplitude like a little bit bigger. So the amplitude here let's call it like, well, I'll call it this. It's A times what we call an amplitude ratio. So if the amplitude ratio is greater than 1, the output amplitude is going to be bigger than the input amplitude. Or if the amplitude ratio is less than 1, then it'll be smaller. Okay. Now, this delay between the signals, we call this phase shift. And if the output signal is like lagging behind the input signal like I showed here, that's called negative phase shift. And really, like any physical system in reality is going to have negative phase shift from an input, because we live in a causal universe where inputs create outputs. So you can't have an output precede the input that created it. You know what I mean? If I push on something, it moves after I push it. So there's always like this negative phase shift where an output is reacting to the input. I mean, the whole flow of this kind of suggests that there's an input that goes into a system, and then the system kind of reacts to that input and boom, plops out this output. Okay. So let's make a couple points from this figure. Important points. Okay, 1. The output has same frequency as the input. Like, that doesn't change for linear systems. If you provide an input at 1 cycle per second, the steady state output will also be 1 cycle per second. Okay. Important point number 2. The output amplitude is related to the input amplitude by what we call an amplitude ratio. So it's kind of like an input amplitude comes in, you multiply it by the amplitude ratio, and that's what your output amplitude is going to be. Okay. The output sinusoid is phase shifted. So there's some delay between the input and output signals, as you can see. How about we write mathematically y of t? So it's going to be a sinusoid, but its amplitude is going to be the original amplitude of the input times my amplitude ratio and then it's going to be a sinusoid with the same frequency as the input, which was omega, but there's going to be a phase shift. And like I said, this is usually a negative number because that indicates a delay. And the input, just to remind ourselves, was A times sine omega t. Okay. So now we're getting close to our experiment. So we're going to see this in action on a real system, this DC motor. But first I want to talk about DC motors just a little bit. So we're about to do our experiment to look at the sinusoidal response of a linear system and see the behavior that I just talked about. All right. Get ready to draw, because we're going to make a schematic of a DC motor. So this is a popular schematic. Actually, I'll draw it this way. Okay, so we're going to have a circuit over here. And this circuit has a resistor. It has an inductor. And then it's going to have something new over here, which is called a transducer. And I kind of draw it with this circle with like two squares on the top and bottom. Okay, so here we're going to have, this is our source voltage. And for motors, it's also called the armature voltage. And let's draw some current going through here. And I'll just call it I. Okay. Now this transducer, it's going to function like a voltage source relative to the circuit. We'll talk about, well, this transducer will make more sense in a second. Okay, now a motor is an electromechanical system. So it has an electrical part connected to a mechanical part. And the mechanical part is a rotor. It's a cylindrical object that rotates about this axis. So we'll say, it rotates that way. and the angle is theta. And it's in this housing called the stator. And I'm going to draw some little like X's in here that represent friction. And let's call the friction coefficient, let's just call it like C. So one of the places this friction can come from, if you've done anything with DC motors, you've heard of brushed DC motors. And so there's actually brushes that act as electrical contact to the rotor. So there's like brushes, they're made of friction equals brushes. Yeah, there you go. And they're not like a hairbrush. They're solid and they rub along the outside. So we'll have a friction force that's proportional to the speed of the motor. Okay. So this circuit, due to electromagnetic force, produces a, if I can draw, it produces a torque on that rotor. Spring-loaded rotational contacts. Perfect. Thank you, Phil. So this produces a torque. But if you, so that's how the electrical system affects the mechanical. When you run current through this circuit, it produces a torque. Actually, let's write the transducer equations real quick, because it'll make more sense of what I'm saying. So the torque acting on the motor, maybe I'll write that out first. Torque on rotor, that's our rotor, we'll call it T, and it is K, which is the motor torque constant, times the current that's going through the circuit. So this is the motor torque constant. So if you have a big motor torque constant, then you get more torque per current that runs through your motor. And if you look at like a motor and it has like a couple amps running through it, that's a lot of current. It probably is pretty torquey. Okay, but when, so that's the electrical system affecting the mechanical system. You run current through it, it produces torque. But the mechanical system also affects the electrical system. Like some motors can act as generators. Or you guys have heard of generators, whatever. Or think about like a windmill. Or I don't want to say a windmill. What's the windmill that's in the water? I can't think of what it's called right now. But you know what I mean. There's current from some river or something, or some creek, and it pushes on the paddle wheels of this thing that I can't think the name of, and it rotates a shaft, and that produces electrical energy. Well, if you have the proper circuitry arranged on the other side. But anyways, an alternator, water, yes, thank you. Yeah, I was thinking like a water turbine or something. Niagara Falls, right? So what that produces is called a back EMF on a motor. an EMF is an electromotive force. So we'll say that voltage on circuit from the rotor, so the torque on the rotor from the circuit, and then alternatively this voltage on the circuit from the rotor, we're going to call it VB for back EMF. So that's KB times the speed, theta dot, of the rotor. So the faster that this rotor spins, it produces a more voltage on the circuit. So this is called the motor back EMF constant. Oh, I didn't label this back EMF over here. So that's this right here. And so this area right in here, we call this the electromechanical transducer. Because transduction is converting some quantity into like a different type of quantity. So the current in the circuit through the transducer is converted to a torque on the rotor. And the angular velocity of the rotor is converted to a voltage back in the circuit. So that transduction is this exchange or like translation of different physical quantities and how they affect each other. So you could call this like the interface between the electrical and mechanical components. And a transducer is not like something you point out by eye in a circuit. Like a resistor, you can be like, oh, there's a resistor, there's an inductor. You can't be like, oh, here's a transducer. This is kind of an abstraction of this physical interaction in the motor. But this is our way of like making a schematic that allows us to do some analysis. I guess for some types of systems you can point out like, oh, this is a transducer, but in the case of a motor, it's just if you run current through these coils that surround the rotor, it produces this torque. So it's kind of like surrounding the whole thing. Okay. So what I want to do is make a state space model. And it'll be pretty quick to do. Okay. Okay. So I want to look at the electrical system first. I'm just going to redraw this really quick because I ran out of space. Okay. Plus minus VB. Plus minus VS, R, L, and the current. All right. So we're going to use the loop rule. Let's make like some little points on here. C, D. So here's our loop rule. The voltage from D to A plus from A to B from B to C, and finally, once again, from C to D, all those voltage rises and drops are going to be equal to 0. We haven't done this in a little bit, so this is a good refresher. Okay, when you go from D to A, you're crossing from the minus to the plus terminal of the source voltage. So that's going to be positive Vs. We consider that a voltage rise. And then we cross this resistor from A to B, but we're going in the direction of the current. Because they're in the same direction, that's considered a voltage drop. The voltage drop is, by Ohm's law, the resistance times the current. We're going to go across this inductor in the same direction as the current, so that's considered a voltage drop. And we just call that minus VL. And then, when we go from C to D, we're crossing another voltage source, but we're going from the plus to the minus. So that's considered a voltage drop. 0. But here's a cool part. We can now use our transducer equation. So I'm going to scroll up real quick. Because remember, VB is equal to the motor back EMF constant times the angular velocity of the rotor there. So let's rewrite this. Vs minus Ri minus VL minus KB theta dot. So now, it's interesting. We have an electrical system which has some mechanical terms in it as well. We have the angular velocity of the motor affecting the dynamics of this circuit. Interesting. Okay. So we also have this element equation for our inductor. And that is, let's go back to this color. The time derivative of the current going through the inductor is 1 over L times the voltage. So let's solve for the voltage from this loop rule equation, which is easy enough to do. We just bring VL over to the right-hand side, and we're going to have Vs minus Ri minus KB theta dot. Beautiful. All right, let's go to the mechanical part now. And that by itself kind of looks like this. I have a torque acting on it, but then I'm going to have, friction, say, from the brushes in here. And that's going to create a friction force. And we said the friction coefficient was C. Let's say the moment of inertia of the rotor is I. That's a popular variable choice. And we defined our angle to be theta. All right, so when we model mechanical systems, we use Newton's second law. And there can be components either rotating or translating. This is just purely rotating. So Newton's second law for, let's just say, a rotating body. It's this. We did the same kind of equation for the pendulum that we did at the beginning of the class. It's the moment of inertia times the angular acceleration is equal to the sum of torques acting on the body. So, well, one torque is just the torque that comes from the circuit, T. And then the friction, we're doing this type of friction, where it's just friction coefficient is proportional to the speed. So the faster this motor spins, the brushes are wearing against the rotor, and it creates more friction. So that's kind of like always trying to slow it down. Here we're going to use the transducer equation as well, because the torque was equal to, let me go back and check, K times the current. So let's substitute that in. K times the current minus, and there we go. So now we have a mechanical equation of motion that has some electrical terms in it. And that's why we call this an electromechanical system. The electrical equations have some mechanical things. The mechanical equations have some electrical things. They're all working together. And I want to bring this all together in one big state space model. And then once we do that, we're going to take a break. And then we'll be ready for our experiment. Finally. Okay. Here's how I'm going to define my states. I'm going to pick one state to be the current. I'm going to pick another state to be the angle of the motor. And I'm going to pick another state to be the angular velocity of the motor. And these are all a function of time. I guess I haven't been putting this function of time, but they're obviously a function of time. You can leave out this middle state, the angle of the motor, but what the heck, let's throw it in. Okay, so that's the first step to creating a state space model. You define your states. We're going to define our input. So I'll say my input U of t is the source voltage to the motor. Why can you leave that out? Okay, because if you look at this equation, you don't see any theta terms. Like if there was some kind of spring force, then you would see something dependent on theta, but there's only damping. So the theta state doesn't affect any other of the system dynamics. Like a spring mass system, the theta state, it directly affects the acceleration of the system because if you stretch that spring. But in this case, I could spin this motor to any like angle and leave it fixed there, and nothing is going to affect the dynamics. Like what I mean by that is like with this motor, if I rotate it over to here, well, it's still just chilling there. It doesn't care. But if I speed it up, I can feel the resistance in my hands. I don't know. We're going to put it in there. Okay, the output, I'm going to choose it to be theta dot. So I have my states, input, output. So let's make our A, B, C, D matrices. Z dot. So I dot. So I'm taking the first derivative of all of my states. So I know my A matrix is going to be 3 by 3. My suggestion is you, in advance, you block out these matrices because you know their size in advance. This is going to be a 1 by 3 here. This is going to be a 1 by 1. And I already know that it's... Wait, is it 0? Yeah, it's 0. Of course it is. Okay. All right, let's fill this in. So I dot was 1 over L times the source voltage minus R over L times I minus, so it doesn't depend on theta, and then it's minus KB over L times theta dot. Theta dot, well, that's just our third state. 0, 0, 1. Theta dot equals 1 times theta dot plus 0 times Vs. And theta double dot, it's going to be K divided by I, my moment of inertia. It doesn't depend on theta. And then minus C over I. And it doesn't depend on the source voltage. And then this one is just going to be 0, 0, 1, 0. Okay, so this is how you model a motor from like first principles. But before we go on break, I'm going to leave you with this. Let's say that I want to use this state space model to model this motor right here. Okay. So I would need to define the resistance of this motor. I would have to define the inductance. I would have to know the motor constant. I would have to know the moment of inertia. I would have to know this other motor constant. I would have to know the damping factor. So there's 1, 2, 3, 4, 5. There's 6 parameters that I would somehow have to measure off of this physical device. Like the moment of inertia, you could run some experiments to like see how this spins down. I think you could also get a good estimate of the damping. The resistance, I think that's difficult to get because the resistance of this can change depending on the orientation, I think. Sometimes we neglect the inductance of motors because it's like relatively small. But all that to say, it takes some work. It's not easy to do, and I don't think it's the preferred method for modeling motors. So the experiment that we're going to run after this short break is what I think is a better method for getting a realistic model of this motor, and we have to measure many less things. So I'll just leave you with that, and let's come back at 3:15, and we'll start doing some experiments. See you in a little bit.
天国を追い出された天使は悪魔になるしかないのだ。そうだろう、スパイ。
Okay.
shopping for the village.
Alright, are you guys ready? Okay. So basically what we got here, this is a 6-volt brushed DC motor. And I have a 6-volt power supply, and what I'm going to do is I'm going to give this a sinusoidal input voltage, and we're not going to give the full 6 volts. I think I'm going to give something like 4.8 volts, and we're going to try different frequencies, and we're going to measure how fast the motor spins as a result. So let's get right into it. Let's close this. Okay. I'm gonna make the frequency 1/10 of a cycle per second. So it's going to take 10 seconds to go through a complete cycle. Let's plug this in.
His name's Asimov.
Okay. Let's see if this is going to work. I'm kind of like juggling because I want to show you this graph at the same time. Oh, wait. One quick change I want to make. Get rid of this. That's better. Okay, so the red line is the angular velocity of the motor. And the blue line is the supply voltage, which is the input. So you see that they're going at the same frequency, but the amplitudes of the signals are different, which, I mean, it makes sense. Like, the blue line is in volts, the red line is in radians per second. So I think it's getting up to about 10 radians per second. How fast is that? know, like maybe 1.5 rotations per second. Yeah, it's a reversible motor. And the voltage is cycling up to about 4.8 volts and then going to negative 4.8 volts. Alright, I'm gonna unplug it. Oh, geez. Almost rolled away on me. Alright, now we're gonna change the frequency. Let's do... Let's do 1 cycle every 2 seconds. So this is 5 times as fast. Well, 5 times the frequency. Alright, I'm gonna plug this in. Let's go to the plotter. Make that full screen. So now the voltage, for all of these experiments, I'm having the voltage go up to 4.8 volts, positive and minus. It looks like in this case the motor's getting up to a similar maximum speed. It's going up to like 10 radians per second. So we're just comparing those input-output signals. Before class today, I recorded data from all these tests that we're doing. And I kind of tabulated it. So we're going to go back and look at all of these. How about we... Okay, let's do 1 cycle per second. And then I'm going to go up to like 3, and then I'm going to go up to like 6 cycles per second. Let's do this. Okay, so I haven't plugged in the motor yet. Oh yeah, so I want to point out this phase difference between the motors as well. Like I told you, the output has to lag the input a little bit. So the voltage is in blue, and you can see that the angular velocity is in red, and it's kind of shifted to the right. Because, it makes sense. The rotor is reacting to the voltage, so it takes some time for that effect to go. Okay, let's pump this up. Let's go 5 cycles per second. No more playing games. Okay. Okay, so you can see the voltage is pulsing 5 times a second. And now you see the motor can't get up to as fast of a speed as it did before, you know? Because the voltage changes direction so quickly that the motor doesn't get a chance to really speed up. So I'm looking at the plot. It looks like it only gets up to like half a rotation per second. Whereas before, it got up to a speed of like one, it was like 3 times faster. Okay, heck, why don't we do one more? Last one. Maybe I'll do 10. Why not? 10 cycles per second. But in this case, the voltage is alternating so quickly, I don't think the motor has any time to like speed up in one direction or the other. You know what I mean? But that's an effect that I want you to see. Okay. 10 times a second. Oh, look at that. It's just jittering back and forth. And it's not really picking up any speed. It has no time to speed up one way or the other. All right. So what you've just seen is one type of a frequency response experiment. Let's go over to MATLAB really quick. I want to... So I saved data from those experiments earlier. I want to show you this. Any reason why it seemed to be favoring rotating counterclockwise when the frequency is at 10? Oh, good question. I think... I don't know, really. Equal and opposite inputs. That's right, like, it should be, you know, producing the same amount in the positive direction as the negative. But like you said, we kind of saw it wandering in one direction. And I'm wondering if it's just possibly a manufacturing defect, or maybe this isn't, like Phil asked if this is a reversible motor. I'm wondering if technically it's not advertised as reversible. Like maybe in one direction it's a little, maybe the brushes are oriented a certain way so that they rub differently in the other direction. That's a good question. It could also be I'm using this Arduino to generate that sinusoidal input. But my Arduino, when I'm running this code, it only works at like around 100 samples per second. So it's only updating its command 100 times a second. And if I'm trying to do a sinusoid of 10 hertz, a 100 hertz sampling doesn't resolve it super well, even though it's still kind of clean. That's like 10 samples per cycle. I don't know if that has something to do with it as well. Okay, let me explain these plots here. These, hopefully you can read this. I don't know if it's a little small on your screen, but these are the different experiments. This is 0.1 hertz in the top left. This is 0.5 hertz in the top right. So, I mean, you can see like each graph is getting higher and higher frequency. But what I want you to notice is the scale, the vertical scale on the graphs is all the same. It goes from -10 to 10. So this orange line is the angular velocity of the motor. And in our first experiment, it was getting up to close to like 10 radians per second. And the next experiment at 0.5 hertz, it was still getting up close to like 10. But as it gets faster and faster, you see this amplitude start to like shrink. Because as we went faster and faster, the motor didn't have any time to really get up to speed. So it's going like slower and slower and slower. But as we saw, like, even though it's going slower, it's alternating back and forth with the same frequency as the input. Like if I zoom in here on the 6 hertz data, the frequency of the two signals is the same. I mean, the output in red, the angular velocity, it's delayed from the voltage. That's the negative phase shift that we talked about. Okay. But what I said was, this is a way for us to get a model of the motor. So I want to tell you how that works. Okay, let's go back here. All right. Okay, so what we did, oh, my pen is killing me. We provided 8 different input frequencies. So our input, U of t, let's call it the voltage, it was about 4.8 volts. That's the amplitude. Wait, let's just say it A first. A sine omega t, where A was just about 4.8 volts and omega was 0.1 times 2 pi radians per second. So 0.1 hertz converted to radians per second is that. And 0.5 times 2 pi, 1 times 2 pi, blah, blah, blah. We went all the way up to 6. So we tried 8 different frequencies. Now, the output for each of these, like we said earlier, it's going to be the amplitude of the input times the amplitude ratio times a sine of the same frequency, but there's a phase shift. And in all of the cases, this phase shift was negative. Like, it was, the angular velocity signal is delayed a little bit from the voltage signal. Okay. How about, let's make a little table. because I want to tell you what the amplitude ratios were, because this is what you can calculate from the experiment. Okay. So we had 0.1 hertz, 0.5, 1, 2, 3, 4, 5, 6. Okay, so the way you get the amplitude ratio, let's look at this graph. Or, okay, hold on. If you compare these things, this is how we get our amplitude ratio from the experiment. Amplitude of output divided by the amplitude of the input. And this is what we're going to use to fill in this table. So, if I go to our first experiment and I like zoom in on this peak here, the amplitude got up to 9 radians per second. Well, over here it got to be a little bit more actually. 9.5. I'm expecting if we let this keep running, it would be like 9.5 on either side. Okay, so that's the output amplitude. The input amplitude, oh, like I said, it's like 4.8. There we go. So, the amplitude ratio for this first one is 9.8, or whatever I called it. 9.5. I will call it 9.8. So if we calculate that, okay, 2.04. That took way too long. So this amplitude ratio was obviously greater than 1. This means that the output amplitude is more than 2 times the input amplitude. Let's do one more together, and then I'm going to fill in the rest of this table for you. Okay, if we go to the second one. Or wait, let's go to the last one actually, or this one. Yeah, let's do this one. Okay. The input amplitude, okay, you can start to see that these signals are a little jagged. That's because the Arduino couldn't sample fast enough. But I think the input voltage still was 4.8. Like, I just didn't sample when that happened, I guess. But let's say the input, or this orange one is the our output amplitude. I'm going to say it's like 3.2 or something. Or maybe on average it's more like 3.4. So 3.4 divided by 4.8. So 0.7. So at 6 hertz, 3.4 divided by 4.8, the amplitude ratio went down to 0.7. The output amplitude is 70% of the input amplitude. That's all that means. Okay, so if you went through and did that for all of these, I'm going to fill that in. So I got 1.8 and then 1.7, 1.5, 1.2, 1.0, 0.9. So we calculate the amplitude ratio for all of our experiments. Okay. It turns out the amplitude ratio, and this is where the relationship to a model starts to emerge, is equal to I have to define something before I do this. Okay. If our transfer function is y over s over u of s, and then let's just like call this by definition like g of s, just to simplify the expression. So like from earlier, what was our transfer function? It was like k over s plus tau or something. So just like that, for example. You have some transfer function, call it g of s. The amplitude ratio is you take g of s and you set s equal to I times omega, where I is the imaginary number, omega is the input frequency, and then if you take the magnitude of this, so these straight brackets mean magnitude, this is the connection between an experimental quantity. On the left, you have the amplitude ratio. We got a bunch of those at different frequencies. On the right, we're saying the amplitude ratio is related to the magnitude of the transfer function for that underlying model, where for S in your transfer function, you plug in whatever frequency times the imaginary number I. I know that's like a mouthful. Well, this, your transfer function evaluated at I omega, this is called the frequency response function. So, in words, this is the magnitude of the frequency response function evaluated at S equals I omega. So if I can come up with a transfer function that has this magnitude profile, well, then I've come up with a model. Okay, let's do an example. Okay, let's take this transfer function that we made at the very beginning. So what I want you to do, calculate the frequency response function of this transfer function. So what you do is you evaluate it at I omega. So where I see S here, I plug in I omega. Usually, we don't like to have an imaginary number in the denominator. So what we do is we do this little trick. You multiply this by its complex conjugate. So I multiply this by minus I omega plus tau. But I have to do this on the top and bottom, so it's like multiplying it by 1. So this is going to give me negative k omega I plus k tau. And let's distribute the denominator. I omega times minus I omega plus omega tau. I'm doing like Christmas colors here. Well, I'm really committed to this consistent color thing. So I just distributed the denominator. This equals over omega squared. Because if you take this That's minus omega times I squared equals minus omega, because you know I squared is minus 1. So this is just omega squared. These terms cancel. And then you have plus tau squared. So we got rid of the imaginary number in the denominator. So this leaves you with oh, I forgot the I term here. So this is the real part of our frequency response function. This is the imaginary part. Okay, let's talk about how you get the magnitude of this frequency response function. So we'll do this. I'll show you the magnitude, and then I'll show you, because I won't have time to go through all the details today, but I'm going to fit our experimental model, our experimental data with a model like this. And just show you that it captures the behavior of the frequency response. But we're going to have to call it a day, I think. Okay. So calculating the magnitude of a complex number. How do you do that? Because the frequency response function is a complex number. So let's say I have a complex number A, which is, it has a real part and an imaginary part. So the magnitude of A is the square root of the real part squared plus the imaginary part squared.
Do you see now?
So the imaginary part, when I say that, it excludes the I term from it. I'm saying it's the coefficient in front of the I term. So this is how you do it. So if I want to calculate the magnitude of this function, this particular function is going to be this. So square root of the real part squared
You see it? I was fluid like water.
plus the imaginary part squared this is going to be, so I could pull out the K, and I'd have tau squared plus omega squared over omega squared plus tau squared squared. Well, this top can cancel with one of the powers at the bottom because they're the same thing, tau squared plus omega squared. So this is K over the square root of omega squared plus tau squared. Okay, so the point is, I ran an experiment, right? And I tested a bunch of different frequencies, and I calculated the amplitude ratio. Well, I know that the amplitude ratio is the magnitude of the frequency response function evaluated at I omega. Amplitude ratio. So, if I can pick parameters K and tau so that this amplitude ratio matches the amplitude ratios from my experiment, then I know that this underlying transfer function describes the dynamics of that system pretty well. I feel like I'm probably confusing everybody because anytime that I'm like, this is coming across confusing to me, it's probably coming across confusing to other people as well. It's just one of those topics. Okay. Let's go back. I want to show... I want to try this first. Okay. I want to plot my amplitude ratio as a function of frequency. Okay, so it looks something like this. These were my slower frequencies. I had a bigger amplitude ratio, and then as I did faster frequencies, my amplitude ratio got smaller and smaller, right? Okay. It turns out the transfer function that I've been showing you, that first order transfer function, it can fit this data pretty well. Okay, let's try this. Because I picked some parameters earlier that I think can do it. Omega. Let's try this. Let's see if this does what I want. Evaluate this. And then do this. Ooh! So check this out. I made a first order transfer function, and I played around with those two parameters, K and tau. And I found a combination that, you know, pretty smoothly matches the data that we were getting. And once you have a transfer function, remember, that's a mathematical model for a system. So I could simulate how this transfer function responds to a bunch of different inputs, even ones that I didn't test today. And that would probably be a pretty good reflection of how the motor responds in real life. And if you go back here, okay, this is one way to model the motor. You model the circuit, you model the inertia, if you can figure out all of these parameters by measuring them in some way, then this will also match the behavior of the system pretty well. But this is kind of hard to do. So I guess what I'm saying is often it's easier to run some experiments and, what am I looking for? And basically make a table like this with amplitude ratios. And I mean, we're running out of time in this course, but I want to teach you some basics of knowing when you can use a first order transfer function or a second order to fit the behavior of a system and get a model in that way. I hope this wasn't too confusing today. I feel like I tried to do maybe too much in one lecture, but the experiment was cool. You'll probably remember that. I'm going to, I think I'm gonna give you guys a break on homework until Friday, because you just finished the project, you finished that other transfer function homework, and today we kind of spread over a lot of stuff, and so I don't know if I'm ready to give you a homework on this kind of stuff. The next homework I'm going to give you on is frequency response functions, but we can dig more into that on Friday. Thank you guys for your attention today. I hope you enjoyed it. I hope you had fun. I had some fun. I'm going to hang out for a bit for office hours if you guys have questions or you're curious about anything. Other than that, I just hope you have a fantastic rest of your Wednesday. And then I'll see you again on Friday.
そのためにはどんな動きにも対応できるように全身の力を抜いて、そう。
I will show the way. right path to find and guide, to find and guide in life.
think I'm gonna call it early today. See you